Quantum wizardry. Room temperature trick triggers quantum effects using light. Imagine altering a material's very nature with just light, a feat once relegated to the realm of magic. Researchers at the University of Konstanz, Germany, have achieved just that, demonstrating a groundbreaking technique that manipulates materials using light, opening doors to advancements in fields like artificial intelligence and quantum computing. But here's where it gets interesting. This phenomenon, driven by Magnon pairs, was never predicted by existing theories. This isn't sleight of hand or illusion, it's a scientifically observed transformation driven by a deeper understanding of the quantum world. The key players in this quantum magic trick are Magnons. So, what exactly are they? Magnons aren't individual particles like electrons or protons. Think of them as collective ripples of electron spins within magnetically ordered materials, almost like a synchronized dance of magnetism. These quasiparticles behave like waves and can be controlled with lasers, offering a potential avenue for transmitting and storing vast amounts of information at terahertz frequencies. And this is the part most people miss. Scientists believe electron spins could be the future of data storage and processing, handling the ever-increasing volumes of information we generate. Until now, scientists could only effectively manipulate magnons at their lowest frequencies. However, the team at the University of Konstanz, led by Davide Bossili, has discovered a way to excite magnon pairs at their highest magnetic resonance frequencies using only light. This is a significant leap forward. How did they accomplish this? Every material possesses a unique set of resonant frequencies, like a fingerprint, encompassing electronic transitions, lattice vibrations, and magnetic excitations. Bossini's team used precisely calibrated laser pulses to alter the frequencies and amplitudes of these magnons, effectively rewriting the material's magnetic properties. As Bossini explains, it's like changing the material's magnetic DNA, temporarily transforming it into a different substance with entirely new characteristics. This discovery was a complete surprise, defying all prior theoretical predictions. Even more remarkable is that these changes are induced by light and not temperature, allowing for modification at room temperature, a significant advantage over many other experimental setups that require extreme cooling. And this is where it gets controversial. While many cutting-edge scientific advancements rely on complex synthetic materials, this research achieved remarkable results using readily available downall, which had been a material used for centuries because their hair has been transferred to a material or one of these many times. This accessibility could democratize the technology. The implications of this research extend even further, potentially revolutionizing quantum research. The team aims to create Bose-Einstein condensates of high-energy magnons using these readily available hematite particles at room temperature, a feat that typically demands ultra-low temperatures. This could dramatically simplify and accelerate advancements in quantum computing. This research, published in the prestigious journal Science, raises several intriguing questions. Do you believe this technique could truly revolutionize fields like AI and quantum computing? Could the use of common materials like hematite democratize access to these advanced technologies? Share your thoughts and opinions in the comments below. Let's discuss the future of quantum wizardry. Scientists rewrite magnetic DNA. Light-controlled magnons breakthrough explained. Imagine reshaping a material's fundamental magnetic behavior without extreme temperatures or exotic chemicals. Sounds like fantasy? Researchers at the University of Konstanz just proved otherwise using nothing but light. By directing bursts of laser pulses at common minerals, they discovered how to control magnetic waves called magnons, unlocking potential for faster than light speed data transfer and room temperature quantum research. Hold onto your science textbooks. This changes everything. Here's the mind-blowing truth. Modern tech is drowning in data. AI systems and smart devices generate information at unprecedented rates, threatening to overwhelm our current infrastructure. The solution might lie in magnons, coordinated magnetic vibrations that behave like digital highways. But there's a catch. Previous methods required targeting low-frequency magnons through time-consuming thermal processes. Enter this breakthrough. The Konstanz team achieved what many considered impossible, controlling high-frequency Magnon pairs to alter a material's magnetic properties at room temperature. Their secret? A clever optical trick involving hematite, a common iron ore used in ancient compasses. By exciting these Magnon partnerships with laser light, they effectively rewrote the material's magnetic fingerprint, creating new properties on demand without generating heat. This isn't just incremental progress. Lead researcher Davide Bossini describes the results of a stunning surprise that defied existing theoretical models. The method allows precise control over Magnon frequency and amplitude, crucial for terahertz frequency data transmission that could revolutionize computing. But here's the controversial twist. They achieved this using readily available natural crystals, not rare earth elements. Could this approach dismantle reliance on expensive, hard-to-find materials in tech manufacturing? Here's where it gets revolutionary. Their technique might enable quantum Bose-Einstein condensates at room temperature, a phenomenon previously requiring cryogenic systems. This isn't just about data storage. It's about opening quantum research doors without expensive cooling systems. As Bossini explains, every material has a unique resonance signature, and their method allows temporarily altering these frequencies to mimic a completely new substance. But wait, why hasn't anyone tried this before? The answer reveals one of physics' biggest challenges: navigating the intricate dance between light, matter, and magnetic excitations. Previous attempts only managed low-frequency Magnon control, falling short of the terahertz push needed for future tech. The Konstanz team's bold approach to directly exciting high-frequency Magnon pairs shattered these limitations. Their work, funded by Germany's DFG and published in Science Advances in June 2025, combines quantum mechanics and material science in unprecedented ways. Using everyday minerals, they demonstrated we don't need space-age materials to push technological boundaries. This opens new avenues for sustainable tech while maintaining high performance, a rare win-win in scientific circles. So the big question remains: could this laser-driven Magnon control create a new era of accessible quantum technologies? Bossini's team shows us that sometimes the most groundbreaking solutions hide in the ordinary. Now imagine researchers worldwide exploring hematite and similar common minerals to build the quantum future. Magic? Maybe. But it's science. What do you think? Is this the future of tech material innovation? Revolutionary tech! Hacking Magnons for quantum domination. What if you could transform a material's essence with just a beam of light? No heat, no exotic ingredients, just a flick of physics. This isn't science fiction. Researchers at the University of Konstanz have cracked a method to alter material properties non-thermally, using light and magnons, opening doors to next-gen tech and quantum breakthroughs, all at room temperature. But here's where it gets controversial. Could this technique redefine how we store data and process information, making today's silicon-based systems look archaic? And this is the part most people miss. The materials involved aren't rare or lab-engineered. They're humble, naturally occurring crystals like hematite, the same mineral that once guided sailors with compasses. Let's dive into the details and spark a debate about what this means for the future of tech. Imagine a material that shifts its identity like a chameleon, changing its magnetic properties with a flash of light. No magic wands or potions required. This is the reality the team led by physicist Davide Bossini has created. By zapping materials with laser pulses, they've triggered collective magnetic vibrations, magnons, that ripple through the material like waves. These magnons don't just move, they transmit and store information at terahertz speeds, a realm currently out of reach for most technologies. The kicker? The process generates no significant heat, sidestepping one of the biggest bottlenecks in modern computing. And unlike traditional methods that rely on rare earths, this approach uses everyday crystals, making scalability and sustainability possible. Now, let's talk quantum. For decades, quantum experiments demanded frigid temperatures. Think minus 270 degrees Fahrenheit, like working in a cryogenic lab. But Bossini's team flipped the script. By coherently exciting pairs of high-frequency magnons with lasers, they've demonstrated that quantum phenomena could be studied at room temperature. This isn't just a tweak, it's a paradigm shift. Could this mean cheaper, more accessible quantum research? Or is there a hidden catch? The paper, published in Science Advances in June 2025, reveals that these laser-excited magnons can alter a material's magnetic DNA, effectively giving it new properties for a fleeting moment. Bassini calls it a fingerprint of the material, one that can be rewritten on demand. But why does this matter for us? We're living in an age where AI and the Internet of Things are drowning us in data. Current tech is straining to keep up, and heat management is becoming a nightmare. Enter Magnons. These collective spin waves could carry information faster and cleaner than electrons ever could. However, there's been a roadblock. Until now, light could only nudge low-frequency magnons, limiting their potential. Bassini's team broke through that ceiling by targeting high-frequency magnon pairs, a move that surprised even the researchers. No theory predicted this, Bassini admits. The result? A material that behaved like a different one, with its magnetic frequencies and amplitudes reshaped by light alone. Let's unpack the implications. Hematite, the crystal at the heart of this discovery, is abundant and cheap. It's the same material that powered ancient compasses, yet now it might power tomorrow's quantum devices. The team's work hints at creating Bose-Einstein condensates of high-energy magnons at room temperature, the feat that could revolutionize quantum computing. But here's the question. Are we ready to replace silicon with magnons? Critics might argue that scaling this tech for real-world applications is years away, but the potential is undeniable. And what about the environmental impact? Using common materials instead of rare earths could make this a green alternative to current tech. So, is this magic or science? It's the latter, but with a sprinkle of wonder. The Konstanz team's work isn't just about faster data transfer or cooler hardware. It's about reimagining the rules of material science. As Bassini puts it, we're not heating the material, we're rewriting its story. Now, the ball's in your court. Do you think this could be the next leap in computing? Or are we still stuck in the early stages of a long journey? Share your thoughts in the comments. Let's debate the future of magnons and their role in shaping our tech-driven world.